Okay, so it is Bevy 0.18. Guess I could pull that up on docs.rs now that the docs are built. Say 0.18, we are good and ready to go. Had the release video yesterday. Today, I want to go back to an example that we did a while ago. And I don't know what I'm going to do. If it's going to work, I'm going to do like a little demo of the little thing that we have right here. I don't know if this is even going to work. I might cut this out later. But I want to do a compute shader landscape today. So we have this old demo. I might put the code here. I might put the code in the Bevy examples repo. But in the Rust Adventure org, we have this demo that does low poly terrain. This is done entirely on the CPU. It has some async stuff going on, and so on and so forth. But generating new chunks is kind of expensive. We did some async stuff because it costs a little bit. So we wanted to, divvy that up. One way that we can greatly improve the performance of this kind of demo is by using a compute shader. And I think this PR hasn't actually merged yet. I thought it might have. No, the PR hasn't merged yet. So this PR has a demo. We're going to check that out. So I'm going to use the GitHub CLI tools, GHPR checkout 22296. I think will work here. And now that as soon as I do that, I remember that I probably have this. Yeah, I already have this checked out. So this will probably just run. Cargo run example, compute mesh. I have the debug features on for some reason. Let's turn those off. So we're going to run this. I've mostly already got it compiling. This is on main right now, but we're going to work with 0.18, the new release. And what's going to happen here is basically this is a compute shader that is kicked off by instantiating kind of like an empty mesh in the regular world, the main world. And that gets pushed into and extracted into the render world for Bevy and slapped into the mesh allocator, which holds a bunch of slabs that hold a bunch of meshes, and thus kind of fits into all of the other pieces of Bevy's rendering pipelines without too much effort. So what that allows us to do is basically instantiate this mesh, upload it once to the render world, to the GPU, and then take a compute shader and actually use a compute shader to do the generation for those meshes. So in this case, there are two cubes, a red cube and a blue cube, as we can see now here with it running on my local machine. And we're basically going to take this example that I built and turn that into some landscape generation. So there are a couple changes from ancient times in this directory. Let me just make a new directory here. We'll do Bevy new. I don't want to call it low poly terrain because we're going on the GPU now. We shouldn't have to do low poly anymore. So we'll do Bevy new. I'm going to call this compute landscape. I'm going to end up with like 3 different landscape demos by the end of the year. We're going to have this low poly one on the CPU. We're going to have a compute shader one. And then we're probably also going to have a mesh shader one. So let's just call this compute landscape for now. We are going to have to make a change here because I think my guess is that nobody made the PR to update this to 0.18. This is a minimal demo, so it doesn't really matter, right? Like this is just main function, app exit, app new, default plugins, that kind of stuff. So we're going to have some empty space to work with here. And there are basically 2 files. We're going to get we don't have an assets directory. I thought that came with an assets directory. I'm just going to call this like landscape.wgsl. It's going to be our compute shader. And then for our main, we're just going to take in the code that's already in there. We will cover it a little bit. Don't worry too much. But the example already has a bunch of comments, so I'm probably not going to go over every little detail. And I'm just going to kick off a compile here and then pull up the code, and we're going to talk about it a little bit while that does an off-screen compile. So we have 2 files here. We have a main.rs and a landscape.wgsl. Obviously, this is going to break, so we need to change this to be landscape.wgsl. We have here default plugins, compute shader, mesh generator plugin, which is our plugin. It's not special. It's something we are going to make. And then we've got this extract component plugin, which is generate mesh. So generate mesh is a component that goes onto an entity in the main world to indicate that this should be a mesh that gets modified by this compute shader. Our plugin here accesses some render world stuff, adds some systems, and then finishes it off. So what we're doing here is in our plugin, getting the render world, initializing some chunks to process resource, in render startup, we initialize our compute shader pipeline, and we add that compute shader pipeline to the render graph. So Bevy has a render graph. You can define like things that you should run before in that graph and some other stuff like that. We have a system called prepare chunks that runs in render. And then we finish off here by grabbing the mesh allocator resource and saying that we are actually going to use this as data that we are going to pass to this compute shader as a storage buffer. So this mesh allocator is really interesting, actually. We're not really going to cover it in detail. But basically what happens here is that there is a bunch of slabs of memory. And whenever a mesh needs to go somewhere for storage, it goes into one of these slabs or a new slab. So what that means is that when we are in the render world, we want to go look up our mesh to use in our compute shader. We have to go ask the mesh allocator for the mesh that we're looking for, or the slab that we're looking for actually. And then the mesh that we're looking for is going to be somewhere in that slab. You can think of this basically as like a vec of bytes or something like that. And at some offset, our mesh starts, and that's all of our vertex data. And we have another buffer for index data that we also ask the mesh allocator for. And to be able to take those buffers and throw them into the actual compute shader, we're going to use buffer usages storage. So our generate mesh is going to have a handle to the mesh that we really care about, the one that we want to generate. And then we've got a setup function and our render world systems down here. Our setup function is fairly straightforward. I don't know that I'm going to keep these comments around. I wrote them all. You can go check them out in the example that I also wrote. So what we're doing here basically is creating a new mesh with at least enough space for the thing that we want to render out from our compute shader, or like create from our compute shader. I think in our case, actually what I'm going to do, thinking about this, is I'm probably going to create a plane here when we get around to the landscape. And I'm going to create this as a plane, make it render world only, and then use the compute shader to modify the vertex height based on some noise algorithm that we choose. In this case, in the like cube case, we are basically just saying for attribute position, which is XYZ, there are going to be 3 F32s. For attribute normal, there's another 3 F32s. For UVs, there's 2 more F32s. And then we also need these indices, in which case we allocate 50 indices. We don't need to use all of the indices. We don't need to use all of the vertex space. But basically what happens here is that we will end up with one giant slab in the mesh allocator that has, starting at the very beginning of our mesh, so at whatever offset that is, it's going to be vertex number 1, XYZ, attribute normal for vertex number 1, XYZ, UV, XY. And here's our current program actually running. So we know that it's working, which is great. We can also look at this in RenderDoc, which is super interesting. But I won't do that today because I'm actually on my Mac. We could do that in Xcode, but I don't feel like opening Xcode right now. So the other thing that we do to this mesh is we are setting render asset usages to render world because we don't need it in the main world. There's going to be some terrain. This is meant as kind of like a easy way to get a mesh into Bevy's render pipeline and do some really custom stuff with it. So we create our mesh here in the main world. We are effectively uploading that. We're adding it to the mesh assets. That goes into the render world. And the main world just kind of forgets about it, but keeps the mesh handle around. So TLDR, this is the amount of data that we have available to write. And this needs to be bigger. It needs to be bigger or exactly equal to what we're actually going to write. We aren't allowed to run over space. We're not allowed to expand the buffer while we're in the compute shader. The only way to change the buffer lengths is to create a new buffer. So this really needs to be at least at what you're going to write or more. Now that said, if you did something like make this way too big and you could fit 3 things in here, you could do 3, meshes. So we've got our component here, generate mesh, which takes that handle that we just created. We've got mesh 3D, mesh material 3D, transform. If you're watching this video, you probably have seen these before. This is the standard PBR material. The indication that we are using a mesh that should render with a 3D camera, as opposed to meshes could be 2D meshes, right? They could render with a 2D camera, which would be a mesh 2D. And this is placed somewhere in the world. And this is how we're going to end up doing our chunking. for landscapes. We are only going to do one level of detail today. I'm not going to implement a whole LOD system. I'm not going to implement, wow, I'm blanking on the name, but there's a thing that happens where if you do LODs with landscapes and chunks, that the edges between two different LODs are different vertex counts. And those seems kind of like need to match up. But we're not going to handle that today. We're going to do one level of detail. We're just going to get this compute shader done, maybe throw an atmosphere on it, something like that. So in this case, it's also interesting to note that we can render this in multiple places. This is generating the mesh, passing the handle into the mesh 3D, but we can also just like reuse that handle somewhere else. So like when we generate this mesh or mutate that mesh data, it is actually the same kind of mesh that we have anywhere else. So if you clone that handle, which we aren't going to need to do, so I'm going to delete that. We also aren't going to need this circle. This circle doesn't matter to us. We don't need a base. We're going to have a bunch of landscape chunks, right? Point light can stay for now. I think this ends up changing to directional light and probably some atmosphere stuff, but we'll leave it for a second. We've got add compute render graph node. What this is basically saying is that we have the render graph, right? Bevy's render graph. And there are labels for what nodes exist. We add our label. So this is the compute node label, which if we click on, we go back up. This is the label. It derives render label, some other really basic stuff, debug, partially clone. And it's just a marker struct basically. And here's our compute node. So also very simple. Nothing really going on here. That's super interesting in that sense. So when we add this render graph node, we add our label with our node. And then we add an edge between our label and, in this case, the camera driver label. Now, I don't think that for our use cases today, this really matters all that much, this little edge here. But it does mean that we will definitely run before the camera. So, I don't think it would really matter to us because there's other places we could place this. But it is nice to know that whenever this runs, it's going to run before things render. So we've got this resource that we initialized before. This is just a vec of the asset IDs for the meshes. Handles, asset IDs, effectively, I don't want to say the same thing. They're not the same thing. But a handle can dereference to an asset ID, which is exactly what we do, as we'll see like right here. Then we've got prepared chunks. There's a bunch of pipeline cache stuff. This is kind of like the pattern for accessing your pipeline in Bevy at this point. I think that happened over the last release. This is prepare chunks. There's very little logic in here. There is basically, we check to see if our compute pipeline has become ready. So on Mac OS, I've discovered that this actually happens basically instantly in demos like this. But on Vulkan, on Linux, this can take a couple frames before it gets ready. So we need to check to see if our pipeline is ready, and we ask the cache for that data. Then what we do is, because we've extracted all of the generate mesh components, which have those handles, into the render world, we can just query them. So we query for all the meshes that we want to generate. We iterate, we get the asset IDs, and we check this extra processed local. So this is local to this system, some state, and it's a hash set of every ID that we have ever processed. Theoretically, is this like leaking memory? Yes. Theoretically, if you spawned enough meshes with the code that I have here, this hash set could grow infinitely, which is something that you might want to care about in the future if you were doing like massive amounts. But for my purposes, I don't really care. I just want a way to say, process this once. So if that process contains the ID, then we don't do anything with it. Otherwise, we let that pass through with our filter, and we end up with basically putting all of the ones that we are going to process in the next step into the process hash set, and then setting the chunks to process to the new chunks that we need to process. This is our compute pipeline. It stores a bind group layout descriptor and our cached compute pipeline ID. If you've done slightly more advanced compute shader stuff, bind group layouts will be very familiar to you. Again, this is not particularly, I don't want to say it's not beginner friendly, but I'm not going into like the basics of compute shaders today. So we're going to initialize our compute pipeline here, set our bind group layout. Well, the descriptor anyway. We don't set the actual layout. That was a recent change too. Here we have a couple of things, data ranges, vertex as a storage buffer, index as a storage buffer. So we talked about those buffers that we got from Mesh Allocator, or we were going to get from Mesh Allocator. This is defining the layout that our shader will actually be able to access. So this is a uniform buffer, which is data ranges. Data ranges is the start and end for the data for our mesh in the slab that we were talking about. So we're going to get a slab. At some point in that slab, our mesh is going to start. These are the indices into where our mesh starts. So we've got that data in position 0. We've got the vertex slab in position 1, and we've got the index slab in position 2. If we take a brief detour to look at our bindings in our compute shader, you can see that binding 0, like we just said, is that data ranges. Binding 1 is that vertex data, and binding 2 is the index data. So we've got exactly what we expected to get in our shader because we set it up right here, right? I've said, I think in other videos and other places, that if you end up writing enough mid to advanced level shader stuff inside of Bevy, what a bind group is and what a binding is, like these are literally just indexes into an array. And here's where we define that array or vec or whatever you want to call it. It's the list of stuff. So we need to load our shader asset. We load our shader asset in. We need to get our compute pipeline ready. We get our compute pipeline ready yet. And then we pass in the layout in the shader. So this is now our compute pipeline in the pipeline cache. And we insert our resource so that we can access this stuff later. And that's our preparation. We prepare the layout, we set it up, and that's all that happens in the init, which leaves us with the really meaty part of the Rust code, which is actually the render graph node. So we have a render graph node implementation for our compute node. Remember, our compute node is basically nothing. It's just a struct, effectively no data. It's got a default implementation, but no real data here. This node, this run function on this node is what's going to run every frame to let us do whatever we're going to do with that compute shader. We get the render graph context. We get a render context, which we get a bunch of interesting stuff from. So if you ever need like access to the render device, etc. We also get access to the world. It's read-only access, which is important because you might think that you can go in here and say, I don't know, build that hash set that we had before inside of this run function, but you can't because you don't have mutable access to the world. So we get the chunks that we're going to process from that resource that we filled in before. We get the mesh allocator, which we've been talking about a couple times. And then for every chunk that we're supposed to process, we get an asset ID. We grab our pipeline cache. We grab our pipeline. As long as our pipeline is in that pipeline cache, we do our work. So this is 286 and that goes down to 363 and there's nothing left. So this is the meat of setting up and running our compute shader. We get a vertex buffer slice by that asset ID. That's why we have these asset IDs in the first place, because that's how we ask the mesh allocator for the vertex or index data, or the slabs that contain our data. So we end up with this slab and that slab. We prepare a couple of things here. There's a couple of multiplications here because of the size of the data. There's a couple comments here that I'll let you go look at the PR or example and read if you want to. But basically, once we get into the shader itself, we're going to be iterating over each individual value, like an F32, and not over like chunks of vertexes, right? Like we're not going to iterate over an entire, what people might call a vertex, quote unquote. But really what they mean when they say that in this context is the vertex, the position, and any other data associated with the vertex. So position, normal, UV for us. Our uniforms, we need to be creating a uniform buffer to actually write our data into, these offsets that we want to keep around. We take that render context that I said was just going to be interesting. We grab the render device, create our bind group, which is binding our data here. This uses our layout. So we get the layout from the pipeline cache for our layout, which we got from a resource earlier. And then we set up our bind group with the uniforms first, the vertex second, or like 0, 1, 2 is what this is, right? So uniforms, vertex, index. This is the same thing we did before. We slack these in here as entire buffers, and then we move on to our pass. So if you're working with render pipelines, you would have a render pass. We have a compute pass. We need to get the command encoder to queue up our compute pass. We say that we're going to begin our compute pass, and it gives us back this effectively guard. So we get this compute pass. In this case, we're pushing a debug group here. This is like literally for debugging purposes. If you ever look at this in RenderDoc, if you look at this next code, this label specifically will show up in those debugging tools. So you really do want to set this, because otherwise you might not have any idea what is going on. And it's nice to have an idea of what's going on. So we set our bind group 0, right? If we look at our shader, bind group 0 right here at the beginning, binding 0, 1, 2. So now we've seen what a bind group is and how we set that, how we set the data for the next execution or the next dispatch or the next draw command, that kind of thing, with our bind group data that we set up. And we're going to ignore this little array here. This is dynamic offsets, which we're not using. We set the pipeline to the pipeline that we set up. We dispatch our work groups. In this case, we're dispatching a work group of 1, 1, 1. So if you think about compute shaders and you think about how they execute, right? You get the opportunity to specify a grid. So when people say they are executing a grid of work groups, what they mean is if we set up 1, 1, 1 here, right? We get one work group which runs a number of threads. If we set this up to be, I'm not going to be able to do this math in the top of my head. If we set this up to like 5, 5, 5 or 10, 10, 10, right? Then there is 0 to 4, 0 to 5 for X, Y, and Z. And you end up with this like grid of global IDs for each work group. So each work group gets one of those global IDs. It'll be like 0, 0, 0, 1, 0, 0, 2, 0, 0. That's what we mean by a grid. So this 3D grid. Now you don't have to use all of them. You can just set this to be like 10, 1, 1, in which case you have 10 work groups. It's pretty easy to calculate. And if you're going to do like a lot of compute, you're going to want to set this to something higher than 1. This is just an example. Then we pop off that debug, and that's about it. So that's a lot of explanation for compute shader stuff. Let's see, in our landscape, we get that data that we passed in, our bind groups and our bindings, right? Our uniform is our static data, these indices into these other buffers. We get our storage buffers, which are these vertex and index data. That global invocation ID is this, the thing that I just talked about. That's like 0, 0, 0, 2, 0, 0, 3, 0. That's this, literally. So vec3 of U32s. This will always be 0, 0, 0 for us because we only have one of them. You can see that our work group size here, this is our thread count effectively, is 1. So we don't have anything interesting going on here. So this is, as far as compute shaders go, this is horribly inefficient because we are running one work group and effectively like one thread. And that's just how it is. But there are use cases to do more than that. I know with mesh shaders, one of the suggestions is to do like 128 because that fits into the like sizes better. There's a bunch of resources and constraints and like different, you know, drivers and devices have different desired sizes for a bunch of these things. There's a lot you can do here. I think you can actually do like const loops and address multiple devices, but all of that's irrelevant for us. And all we are going to do is imagine this loop runs once. This has 192, which is just hard-coded down here. So this is 192 items. If you want to look at these little pieces of data, you can. This is all of the vertex data. So X, Y, Z, this is the positions. These are the normals. And these are the UVs on the right-hand side. This is the front face, back face, right face. This is code that's taken directly from the way that Bevy builds its own cube. So if you do like cuboid mesh new like .mesh.build, this is what you get effectively put on the CPU. So I think we're actually not going to need really like all of this for the most part. The question I have in my head is, how do I want to set this up? I want to set this up to be a plane. Let's get our thing back over here. So we've taken out a couple of things. We only have our cube now. In this case, if we go back up to our spawn here, this cube is like whatever it is. I want this at 0, 0, 0. I just want it centered in the world. It doesn't really need to be anywhere special. This is going to be a piece of landscape, right? So you can place this kind of wherever you want, but you can see how it's changed here. And you can see that we're processing mesh ID or index 3 generation 0. That's the mesh handle for this cube. So let's start off with changing this. I think that off the top of my head, if we do a plane here, that should work. So let's do let mute mesh equals plane, is it plane 3D? Plane 3D new. This is a vec3 and a vec2. Normal is vec3 y, so we're pointing up for the normal. Half size is, what are we going to make the half size? Let's make the half size like 10. We're going to hit dot mesh on this. We're going to hit dot subdivisions. How many subdivisions do we want? I always forget what this number exactly means. This is 0 is 4 points. 1 is half split, so it's 2, 2, 2. It's the end of my day, and my math is not going to be making it here. Resulting in a plane with 9 quads, 3. So this is the number of lines that split our vertices effectively. So if we have 1 line, we have 3 vertices. If we have 2 lines, actually our corner vertex is I'm doing the math in my head based on faces and trying to say that number and being like, that's wrong, that's not vertices. So if we have 2, then we have 3 by 3. If we have 5, then we have 6 by 6, so on and so forth. I don't think this really matters all that much because, and the way that I'm thinking about this right now is the indices for us are not going to change, right? Because we're going to have a plane, it's going to be pre-computed, and really what we're going to do in the compute shader is modulate it once, right? For each chunk. So when we do this, we can specify how high of the resolution it should be. And I want to make that variable. I don't mean that I want to make it variable as in like, we should be able to change it on the fly and have things re-render. I mean that we should be able to configure it from the start. So I think that for this, anything would be okay. And then I'm just going to call build, I think is the last thing here. So this is a mesh. This is supposed to be a vec2, so vec2 splat. And I think I want to be able to set this. Can we set this like right away? This is a mesh dot asset usage. There we go. So I'm going to set this to render world. We are going to just comment this out. Oh, I guess I actually already set this down here. I don't know why I reset that. So we've got a plane now. It's got 5 subdivisions. It does whatever. Let's just run this and see what it does. Now, this should be less. Yeah. So this is less data, or no, that's wrong. Yes, it's less data. Which means that we still have data left over after creating our cube. If I turn this into 0, I think this consumes it completely. Yes. So if you think about this, right? If you think about what's happening here, we are generating a cube in the compute shader, right? When we generate that cube in the compute shader, what we're doing is actually overwriting data that we don't care about right now, which doesn't happen to have any negative effects right now, but just keep that in mind. Keep that in mind that we are going like over bounds right now. But we have created a plane that is effectively a quad. So there's like 4 vertices here, right? When we go to build our cube, we are iterating over all of the vertex data, right? So if you think about the first 4 vertices, that's this chunk of vertices. So if we only have 4 and our mesh is 4 vertices big, then what happens here, along with the indices, but what happens here is we end up setting all of this data. And then because we aren't actually checking what the end range should be here, we're just overriding whatever comes after it in the mesh allocator slab. So all of this is just getting written somewhere. Now that doesn't matter to us right now because we don't have any other meshes in the scene, but keep that in mind because you do actually need to try to prevent yourself from writing over. So we might actually need another configuration option here. We might need to pass through some data through that generate mesh component and try to know ahead of time how many vertices we're going to actually be writing here. because in our case, we aren't going to change the size here. We're going to have a perfect match. So if we have an empty mesh here, right, and we get dot indices, and I'm going to unwrap this because this always has to exist. We should be able to do dot length, and I should be able to debug this. And what I should end up here with is what, a length of 6? Yes. 6. So we have 4 vertices. Why is it 6? We have 2 triangles, right? I don't know the way that we're looking at it right now where the triangles exactly are. We could turn on like wireframe mode or something and figure that out. But basically, one half of this front face is a triangle. The other half of the front face is a triangle. So we end up with 6 indices because we need to specify 2 triangles, which are 3 vertices each. So we can just get that number. So when we have that number, we might be able to expand a generate mesh, which would then hold like our handle. So let's say this is mesh handle, and this is, what do I call this? I call this num vertices. What else would I call this? Let's make this a U32 because I think that's what the indices already are. Cool. So in this case, we have to know ahead of time, which is fine. I'm choosing to make that a constraint of what we're doing here. And then this is going to be this number. Actually, that's going to be U size, isn't it? Because it's length. Let's make that a U32. Force that to be a U32. We don't really need a U64. This is used, I think, is what that means. So value borrowed here after move. That's because we move it here when we add it to that mesh. So I'm just going to snake this. Let num vertices equals this. Name this num vertices as U32. We're going to get rid of some of these comments because these comments are going to be less and less relevant as we move forward. So the question here is, we have our generate mesh. We have some code that uses generate mesh, some code that is no longer working because we're using Rust, right? So Rust is telling us that there's no field.0 on generate mesh here. So this needs to be .mesh handle.id. And what we can do here is actually num vertices or something like that, right? This is going to be what, U32 asset ID mesh. So technically speaking, if for some reason our mesh changed and there was a different vertex number that was put in here, this could fall through our little cache here, but that is totally fine. So this is not going to be that. This is going to be gmesh.num vertices, and that as a tuple. I guess we could keep the whole thing here. This is looking for the whole ID. So process contains that whole ID. This hash set then needs to be a U32 in the asset ID. So now we are good to go for the most part. Chunk data is no longer accurate because chunks to process is holding that same data. So I could have made this a type alias is kind of really what I'm realizing here. And then all of these things would have changed when I changed that type alias. But I didn't think that far ahead, so we didn't do it. So we've got data ranges here, and data ranges are here, and I want to add num vertices here, which is going to be a U32. So here we have num vertices, and this should be, this is going to be mesh ID dot 1, which is the ID. This is going to be mesh ID dot 0, which is our num vertices. I think this needs to also get this multiplication. I'm thinking about this off the top of my head. The number 8 was for 3 position, 3 normal, 2 UV. That combines into the number 8, which gives us this number. This mesh ID.0 is also the same number. Why is this? Oh, because these need to be then cloned. Hang on. Let me check what the compiler is telling me here. I guess I need to be explicit now because these are no longer copy is really what happened here. So we've got mesh ID.0 here. I've got, this is the total number of vertices. I think we have all of the attributes. Let's actually check. I think we will have all of the vertices, all the normals, all of the UVs are all set for this plane. So I think we're good to go. I think we have 3 position, 3 normal. We probably want to set the normal at some point. So we're probably just going to start with position for today, and then we'll go back and maybe set the normals and do some other stuff later. So this vertex count, what are we actually going to use it for is really the question. When we have num vertices, we are going to need to go over a number of pieces of data. And I think we need this actual number because I think we're going to need to loop over those in batch and not not as individual numbers. So I think we're going to leave that as it is. I think everything else works. The downside here is num vertices. It needs to be here. And then there's kind of an open question. What do we do here? This is going to be a for loop, but it's going to be a for loop for data range num vertices, right? 0 to num vertices. We're going to get rid of this whole comment because the comment is not really relevant. I'll go back and write different comments effectively. This index logic is no longer relevant either because the only thing we're going to touch is actually the height data for the position. So we iterate over this, and what we are doing is we need to get I times 8, I believe, because I is going to be num vertices, right? So 0, we start at 0, 8, we start at 9, so on and so forth. We want to iterate over that whole batch of the size of the vertices, which is why it's important that you know what data is in your mesh. If you don't know what data is in your mesh, you don't know how much data to skip over, and you can just start overwriting things you didn't mean to. Significantly less safe doing GPU programming than Rust. So we end up here. Yep, so we're still recording. We end up here with vertex data times 8 plus data range vertex start. So that is our offset in the slab. We have each of our positions. We need probably this. Let's call this offset, right? Offset equals I times 8. Offset plus vertex start is probably really, we want this whole thing here. And this is going to be offset. And this will be not setting that data yet. So we start at 0. And this actually does need to be, we need to fetch this data first. So let's let x equal vertex data offset, right? Let's let z equals the vertex data offset. And let's set y based on I. Let's do, this is going to be offset plus 2, right? Because we are going for the z coordinate there. And then this vertex data offset plus 1 is our y coordinate. And this vertice is no longer going to be relevant. So all of this down here can get deleted because we aren't hard coding this data anymore. And what this turns into is what? I think we're just going to set this to offset. So we end up with a loop here that I believe we are getting the vertex ID, right? Times 8, which is the size I expect the vertex data to be, plus data range vertex start, which is our offset in the slab, which gives us the place at which we should be to access our vertex data. We access x and z, which we are going to use at some point here to do some noise stuff. But for now, we're just going to set this y coordinate to offset. And assuming I did everything right and didn't make any mistakes, which, never happens, and it didn't happen this time either. Automatic conversions cannot convert elements of U32 to F32. What do we have? That's a U32 here. I times 8 times that, and offset needs to be an F32. So offset here, when we're setting this data, when we set the data, it needs to be an F32. And that's what this, there's no automatic conversion there. So my assumption here is that this is like careening off into space. There was nothing there on the camera, but this is going to be like 1, 2, 3, 4, 5, 6. So it's going to be like very large. So let's divide this by 10. Arbitrary number, just trying to get it back in range. This needs to be outside of the cast, right? F32 over 10. I think I saw it briefly. So maybe let's zoom the camera out. Where's our camera? What I like to do is just multiply everything by 10 when I'm doing this, because then I can divide it by 10 later and put it back where I wanted it in the first place. So there's our plane. Can we get our features Bevy file watcher? Bevy file watcher? Bevy file watcher? Oh wow, this is going to be like an hour-long video. You know what I realized as soon as I started doing this is that file watcher doesn't actually help us here. It could if we were generating this every frame. Actually, you know what? Let's do let's do that for a second. Let's generate it every frame. Okay, so there's a plane. If I am doing this correctly. We are reloading our landscape. So let's make a change here in process. So processed is a local. If we just don't check that ever, and we always return all of the IDs that we and we always return all of the IDs that come in. And when we run this, this is generating every frame. You can see the logs spewing out there, which means that I should be able to get a couple of changes going on here. Now, this is not super interesting. Why is this not super interesting? Because it's like 1, 2. Like the change here for this plane, how big it is, it's like 1, 2. So let's make another change here and do our plane. This is going to be a splat of, I don't know, 25, let's say. And let's say the subdivisions are like 50. I have no idea how this will perform. Random numbers that I feel like are potentially interesting. So because this offset is probably, I don't know how many vertices there are here. Actually, now that I think about it, I'm really flattening this out. This is going up way high. So this offset probably should just be divided by num vertices, which is also a U32 if I remember correctly. So let's do that. And then we get this here. So this should be generating every frame. We haven't really passed in anything interesting here. So maybe my question here is actually, did I mess up and pick the wrong distances? Num vertices, we didn't multiply, right? Right, this is num vertices. Let me re-engage with processed just to do some debugging here. There we go. No definition in scope for num vertices. So the issue with running logs over and over and over is that those logs obscure problems that you may be having. So offset over num vertices should be a number between 0 and 1. And I feel like I'm vaguely surprised that it feels like it's not. We've got 15,606 vertices. That is a decent amount of mesh. So my next thought is maybe I actually got my plane wrong. I think plane only has the 3 attributes, but that is not necessarily true. I don't want to generate tangents. That'll create more data. What is the thing here? This is empty mesh attributes for adder in this. Let's debug adder just to make sure that I actually understand. I assumed the layout of get this all the way back down to 0 just to get the data to be a little bit smaller while we're working with it. And what we have here is the logs for a float 32 by 2, which is the vertex position, a normal, which is a float 32 by 2, and a UV, which is 2. So we do have the data that I thought we had. The question that I'm asking myself is, am I inserting it into the right positions? I kind of am, right? For some data, I am actually inserting. So let's do a run here. See, this goes way up. That goes way, way up. And our camera is pretty zoomed out, right? We're at like negative 25, 45, 90. So I think what's happening here is that the plane, when it's constructed, uses this. So let's make this 5 and assume that makes it go back down. It did not. We may be running this next code after all. This is 0, right? So this is 0. If our offset is, let's say, there's 6 vertices here. That may be the issue with this, actually, now that I think about it. A bunch of our vertices are at the same point. So trying to do this little sneaky thing that I tried to do, actually, I actually don't think that works. So let's just go straight to noise. Or actually, we have another option, kind of have another option. We could do X plus Z, which in our case is going to be like not super useful because currently we're doing subdivisions of 0. Yeah, the vertex positions that come in here are actually massive. Significantly more massive than I had in my head. For some reason I had in my head that these were going to come in as 0, 1, but I think the plane actually sets up positions that are the full size of the scale of the plane. So if we do like X plus Z, this is actually going to be like 45 or something, which is a lot. So the real question here is, if we are 50, then the max value here can be 100, right? Yeah, there's an angle. There we go. Okay, so what is actually happening here? I think if I update this to 20, this doesn't change because I confused myself and re-enabled our cache. I don't know, I don't know why I did that, but I re-enabled our cache and forgot about it, which meant that this was not regenerating every frame. So now when we make our changes, this will actually generate. So this is clearly, now we can kind of like play with this a little bit. The thing that I am interested in, I'm going to add Bevy shader utils, which is a crate that I created that is just a couple of noise functions. It's nothing super in. Where's my Chrome window? I never have a Chrome window. Everybody who's ever seen me stream knows that I never have a Chrome window when I need one. So this is Bevy shader utils. I think that I've kept this documentation up to date. We're going to grab shader utils plugin and dump that right up here. This is going to come from that Bevy shader utils plugin. This is just providing, oh, you know what I did? I didn't add the release candidate. This is 0.9.0, that's a 0. 0.9.0 rc.1, I think is what I named this. So that is the 0.18 version. That's why this was an issue. I don't know what compiler message we would have got, but something about like mismatching traits or something like that. Probably mismatching plugin trait. So we have the shader utils. We can go into landscape now, and I should be able to, let's do simplex 2D, I think. Sounds good to me. Simplex 2D, and then the usage is basically just pass in a vec2, get an F32. So let's do vertex data, offset +1 equals, we're gonna update this to have Bevy simplex, or Bevy shader utils. We are going to set this to a vec2. This vec2, we could get the UVs, right? We could go 0 to 1 on the UVs. In this case, we're going X and Z, which is world space positions, right? We have positions, we have normals, and we have UVs. We could use any of that data. Here we have X and Z, which, assuming I set everything up correctly, which, as we discovered earlier, is not always true. RC.0, I named it RC.0. Why did I name it RC.0? That's such a weird version. This is one of those crates that like, it's a couple of shader functions. It's not super important, so... But I can already see a problem here. Bevy pointer 0.17.3. Why? Because I messed up my cargo lock. So Bevy 0.18 came out today. And something that I just installed is trying to pull in 17.3. So I believe that is just going to be my crate that I messed up somehow. So cargo tree-i Bevy at 0.17.3 will give me the Bevy 0 will give me the things that caused Bevy 0.17.3 to be included. Cargo tree-i some dependency will give you, the versions of it that are in your package. This is Bevy shader utils. Is this supposed to be 10? We're taking a slight detour because I really thought I published this. Maybe I just updated it locally and didn't publish. Did I really? I updated it locally and then I just didn't publish it? Okay, well, we're going to take a minor detour into the libs directory with Bevy shader utils. And this is how you publish a crate, ad hoc. So we're going to run cargo publish here. This is probably going to be an issue because it's a dirty directory. So it's going to tell me that. I'm going to allow dirty here because I'm kind of doing this on the fly. So this is going to do a build and a publish for this specific crate. So in this case, it's Bevy shader utils. Bevy shader utils is a library of shaders. It is set up in a specific way. So all of these have UUIDs, handles, etc. The way this is all set up is as load internal asset. And then the way that you use this in a custom material is because I set it up like that, because it has all these defines, we get to import it like this from Bevy shader utils and the relevant package and whatnot. It's cool. I like it. We should upstream noise utilities in WGSL to Bevy at some point. Cool. And right at the end, we see that the publish was successful. So let's go back over here. And this is no longer an RC version. So this can be a cargo update, or I can just delete the lock file, both work. We run here, we basically got all our dependencies already around. So this is super quick, even though we completely installed like a new crate, right? And already you can see the little, I don't know if you can really see it, but you can see the little like curvatures on the sides. So this is still generating every frame, right? So if we wanted this to be more intense, we could make this .10, and you see how it gets really spiky now. Let's see, this is subdivisions 10. Let's do subdivisions 1,000. Let's start cranking this up quite a bit. This is a compute shader, so it is generating, for us, it's generating every frame. The one thing that I shouldn't do is log out all of the data as I bump this up. So I'm just gonna break that terminal. And we're gonna get rid of these debugs, because these debugs are mad expensive. Actually the most costly part of our current application was actually logging those debugs out. Now this is also going to be very big. This is 1,000 by 1,000. How much is 1,000 by 1,000? It's 1,000,000 vertices. That's quite a big buffer. 1,000,000 times 8 is 8,000,000. So we've got 8,000,000 F32s, however big that is, for this. We don't really need that much. If we cut it down to something a little bit more reasonable, because theoretically we're supposed to be chunking this anyway, right? Then you can see that we get quite a bit more going on. This is still pretty spiky. We aren't like updating the normals is another thing. And our point light is kind of like reaching the end of its life here. So instead of going with like just a directional light, right? Let's take a look at the atmosphere example and just go grab it. I'm just going to slot in a couple of resources. Maybe we throw in a camera here. That could be cool. The free camera plugin now exists actually in Bevy. We do need to enable it. So we need to both bring it into scope, which is not in scope currently because we don't have the feature enabled. But we also need to version equals this, features equals, I think free camera is the feature name. That looks right. This should now show up. Yep, bring it into scope. And now we have a camera, which is cool. We'll be able to fly around our scene actually now. There's a bunch of like atmosphere controls and stuff that are in here, but this is not what I care about. I care about these things. So we're going to go down to our camera and slap a bunch of these on and see what issues arise. So atmosphere Earth-like, there's a bunch of custom scattering medium stuff in Bevy 0.18, which is sick. We get an atmosphere environment light. We get some volumetric fog. We turn off one kind of anti-aliasing and turn on a different kind. Screen space reflections, sure, we don't really currently have much of a use for them, but let's see. Maybe we'll be able to steal the water from this example as well later. But we do need scattering mediums. If GitHub would let me actually click inside their UI, that would be sick. So free camera needs to come in, yada, yada. Let's say that we are going to not generate this every frame anymore. Let's say that we are going to generate this once. Again, this is on my Mac, so it's it's not using, an RTX card or anything like that. You know what I'm realizing? I forgot the directional light. And they build a custom cascade shadow config. I don't really think we need a custom cascade shadow config, but it doesn't hurt. We'll bring in Lux to define how strong this should be. I'm not sure how strong it's going to be for our scene, which is like a totally unrealistic kind of scene. And then cascade, we're just going to use the values they had in the example for now. There are defaults. The defaults are fine. Here is our new stuff. And then I don't think we really need to multiply this by 10. So we end up with something that is kind of big, has a bunch of variation in it. I don't think we have much visibility into that because we aren't updating the normals. And thus it becomes a little bit harder to see. Oh, you know what this is? I know what this is. This is the fact that no, this is fine actually, if I remember correctly, because we're doing it in a compute shader. What I thought this was if you do vertex manipulation in a vertex shader, you also have to do the same vertex manipulation in a prepass to get everything to look right, to get SSAO to look right, etc. But I don't think that's what that is. I think that is just things that are in places. It is hard to see without changing the normals, right? If we go into the middle of this like plane, this plane is just like a huge morass of singularly colored stuff. Technically speaking, to do normals, so you can see that gleaming off the side, to do normals correctly, we would have to access the neighboring vertices, which would make the light look significantly better. I feel like we didn't do that in our low poly example. If we do something like generate tangents, then this should break in a way, but you can see some interesting differences just from generating those tangents. So now you start to see like, okay, there's actual like variance here. There's actual change in what would theoretically become our landscape. There's ups, there's downs here. The sky is gleaming off of it. We're getting closer to something that could actually be called terrain. There is, of course, a lot of work to do to get this to actually be terrain, but I think I'm going to leave that for another video. I think that we have kind of covered what I wanted to cover. I wanted to cover that compute shader mesh generation. We are now calculating this mesh based on that data. And now that we can actually see with the environment that there is a bunch of variation here, we could start considering like what would actually happen if we did more or less, or like what this should look like. One thing we could do here is like divide this by 10 instead of multiplying this by 10 and see how that like smooths out the height. But what we would actually want to do is apply that to our coordinates, not the height, because we want our height to be, you know, like 1 or something like that, right? Really change the direction of this camera so that it starts over here. And now you can see that we've got something a little bit more like smooth waves. There's still a little bit going on here where, you know, we aren't updating the tangents, we aren't updating the normals, we aren't updating a whole bunch of stuff here that would make the lighting hit better, because the lighting does depend on these values. But we would need to calculate derivatives in some way to get that to happen. So I think I'm just going to leave that for today. And this is going to be our compute shader mesh. And maybe we'll come back in the next video and do some chunks of this around a map and stuff like that. So I hope you found that interesting. If you have any questions, obviously leave them in the comments. There's that example on the Bevy repo. This code will go somewhere. I'm not quite sure yet. I think it'll go in the Bevy examples repo, actually. So that's probably where the link in the description will go tomorrow. And I will see you in the next one for more Bevy 0.18 stuff and Rust stuff and things like that. Have a great rest of your day.